thought that it was like the CH2 and the C and then the O, like the CH2 below it, and I thought that was a ketone. How do you know which one to go with?
Okay, so what you want to look to tell an ester from a ketone. So look at on here, see the ketone? Ketone is carbon, 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 and a double bond oxygen sticking off. An ester is a carbon, oxygen, carbon with a double bond on one of those carbons. So look at them side by side on that chart. Do you see like the difference? So the trick that I would use is when you see a double bond oxygen in the middle of a chain, look at the carbon and look to see what's attached to that carbon. Are they both carbons attached? Then it's a ketone. But if one of those is an oxygen that's part of the chain, that makes it an ester.
So there's got oxygen in it.
If there's an oxygen in the chain, it's an ester or an ether, right? So notice how that one like spans through. So do you see any other oxygens? One below, okay? So do you see this one? Okay, so this is an oxygen. When I look at carbons on either side, do they have double bond oxygens? No, so that makes this is an ether. Okay, so everybody see this oxygen. See the difference between the ether and the ester? Well, I mean, you could circle the whole thing, but it's because of the position of that oxygen that it's an ether. And it's the carbons next to it. There's nothing but carbons. So that's why I would just circle the oxygen. Whereas the ester above, because there's two oxygens, I end up circling the carbon because it's attached to those two oxygens in the ester.
Okay, will we get it wrong if we circle the CO?
As long as you identified it, but what you can't do is you can't take and say that, okay, this is an ether and this is a ketone.
Oh, okay, yeah.
Okay, so that would be an error because together they're actually an ester. Okay, so that's why it's really a matter of becoming familiar with, okay, if I see a double bond oxygen in the chain, I know that it's either a ketone or an ester. You just have to look at what that carbon's attached to. Are there oxygens on either side? If not, then you know that it is an ether.
So we don't have to circle the whole thing.
Right, as long, like, in reality, if you like pointed to it and you said this was an ester, I'd be fine with that. Right, so if you pointed, it's just circling this whole thing, those two oxygens are the reason it's an ester. All right, one more. What is one other thing that's not just single carbon to carbon bonds?
It's a hydrogen and carbon and double carbon.
This one, right? So we said all single bonds are alkanes. If there's a double bond, that makes it an alkene. See that up in the top left? All single bonds, which is how we've been doing all our naming, is all single bonds and carbons. But if there's a double bond, that is an alkene. And if there was a triple bond, that would be an alkyne.
So those are functional groups too?
Just because they're things that are different than just the norm. Okay? Okay, so this is actually the same one that was in your PowerPoint slide. So here's one other. Here's one other to practice to see. So 1,2-dichloropropane, draw it, give its Lewis structure, do its condensed structural formula. You can do it skeletal if you want. Okay, this is one of those drawing ones, remember, so we did this like first thing last time. So 1,2-dichloropropane. It should be, wait, no. This is my life. This would be slide 18, so it would like be on page 6. If you had, it depends on how you printed yours. So draw these. 5, 6, 7, somewhere in there. It's not one that was changed. Remember, we did these ones as examples. But I told you that I was going to skip this one and that we'd just come back and make sure everybody could do it. So if you see 1,2-dichloropropane, what do you put down first? Propane. So what do you draw? What are you going to need to put down? 3 C's. So carbon, carbon, carbon. because that takes care of that. The last word tells you the number of carbons that you put down for your chain. Remember that that means that each of these carbons has something sticking up, down, left, and right, right? Because carbon has to have 4 covalent bonds. And with us, we're only doing single bonds. So now, 1,2-dichloro. So you can number it, 1, 2, 3. You can number it in reverse, 1, 2, 3. Doesn't really matter. But off of carbon 1, you're going to hang a chlorine. Off of carbon 2, you're going to hang a chlorine. And then that covers this 1,2-dichloro. We've already done the propane. That's it, right? So all those dashes are what? Hydrogens. Any place that you don't have a hanging group, those are just hydrogens. Remember, that's not given in the name. You just know that carbon has to have 4 covalent bonds. So any place that doesn't have something at the end of its bond has to be a hydrogen. Doesn't matter where you hang your chlorine. You could hang your chlorine on the outside, up above or below for carbon 1. It could be above or below for carbon 2. It won't change it because remember, these molecules can flip around. These molecules are not like stuck. So if I had the 3-dimensional molecule of propane, all I'd have to do is just rotate. Remember how you could rotate the single bonds freely in a tetrahedral? So now if I was going to do this as condensed structural formula, how many hydrogens around carbon 1? CH2, and then the chlorine would hang off. Then I would put, for carbon number 2, it would be CH, because there's only 1 hydrogen, and there'd be another chlorine hanging off, and then the third carbon would have CH3. Okay, so you're just putting them straight. So the chain goes sort of straight, every carbon with the number of hydrogens attached to it, and then hang off the chlorines. You could hang them both down, you could hang them both up. I'd be fine if you stuck one off to the side, don't really care. So you really, all you got to do is make sure that there's a carbon with some kind of line to carbon 1 and a chlorine with some kind of line to carbon 1 and carbon 2. Now, the skeletal structure for this is kind of ridiculous looking because that's what it looks like, right? It'd either be a V or a TP, right? So that's 1, 2, 3. So then where would the chlorine be? 1 on 1. So this is a chlorine, and 1 on 2. This is a chlorine. Okay, so remember that those lines wouldn't be carbons on the end because that's the bond holding that chlorine on. Okay, so practice these ones. I will tell you one more time when you go to do mastering, if you have to draw any of them, the trick with the drawing, the chem draw in the mastering assignments, put the atoms down first. So put all your carbons down, put all your hydrogens down, whatever they're telling you to draw, put those down first. Then go to the little single line, which is the bond. When you hover over one of the carbons, it'll like turn blue. Left click. Drag to whatever you want to connect it. When you let go, that'll form a bond. Okay, so first put the atoms down, then put the bonds in. If you have to put non-bonding electrons, you'll see like they look like little dies because it looks like 2 dots or 1 dot. Those non-bonding electrons, if they wanted you to do that, do those like last. Okay, don't worry about putting those in until you've put your atoms down the way you want them. Then do the bonding link. And then add any non-bonding electrons if they tell you that you have to, okay? All right, so we got that one. Well, that's not what I meant to do. So then we just went about functional groups, lots of information about functional groups, okay? This is really like, use this. I did give you sort of some examples and things, but use this page as you kind of review them. You can go back, remember that the unmarked PowerPoints are in Moodle, so you could like download, open up the blank PowerPoint, and you could go back and practice these ones and check them, okay? So you've got them in your notes, you can check them, just a way of being able to practice. Can I actually pick these out? Can I see them? Am I like identifying them correctly? So we did this one, then we did this one, then we did this one, and this is the same one that we just did. This is actually on that handout, so if you have your PowerPoint, you can practice this one later and see if you can actually identify all of those functional groups and then check yourself. All right? All right, then we start talking about isomers. So remember that isomers are just molecules, might be pairs, could be triplets, could be four. You could have lots of isomers depending on the size of the molecule, but they have the same formula, but they either look different or they're drawn differently or they don't have free rotation. So there is some reason that there's a difference in their appearance or their name. So this is where we came up first pair with structural isomers and conformational isomers. So structural isomers, we could identify because they have two different names, okay? You're looking at the way that the bonds are put together. One of your homework problems asked you to identify conformational versus structural versus not related. Conformational isomers, and those ones have like oxygens and nitrogens, that's okay. You don't have to name it. What you want to try to do is just look at how the atoms are put together. So if you see it's a nitrogen to a carbon to a carbon to an alcohol or an OH, and you see the other one is a nitrogen with an OH hanging off, you can see the connections are different. That's a structural isomer, as long as they have the same number of atoms. So I always count the number of carbons, count the number of nitrogens, number of oxygens. If they're not the same formula, then you would just say it's not related. But if it is the same formula, then look at the connectivity. If you can't name it, just look at how the atoms are connected. I think one of the examples had an ether and an alcohol. Clearly, those are going to be different molecules. The ether is when that oxygen's in the chain. The alcohol is when the OH is hanging off. So they could have the same formula, but it's clear if the connections are different, that's a structural isomer. Whereas if you see one, they have there, the bent versus straight chain of butane, they look different, but they're actually put together. They have the same bonding connectivity. So you might see one where it's carbon, carbon, carbon with an alcohol, and the other group is carbon, carbon, carbon with an alcohol, but they look like they're on opposite sides, but you can see the connectivity is the same. That's the same molecule, okay? And if it's the same molecule, just drawn differently, that's a conformational isomer. So we did a couple of these ones pretty straightforward because these ones are just the way we've been naming, nothing extra, nothing fancy. So this was the one that I left. So you tell me, are these molecules structural isomers, conformational isomers, or are they not related? Okay, so you got this because what did you name the top one? 3,4-dimethyl, right? So 1, 2, 3, 4, 5, 6, hexane. Okay, longest carbon chain is 6, that's a hexane. Hanging off of, if you number 1, 2, 3, you get to a methyl, or 1, 2, 3, you get to a methyl. Doesn't matter either direction, the numbers are going to be the same. So this would be carbon 1, 2, 3, 4. So that is why this is a 3-methyl, and this is a 4-methyl. So you put them together to make 3,4-dimethyl hexane. Looking at the one at the bottom, it's easier to see the straight chain of carbons. Can you see that, that these, there's 6 here, so that's also a hexane. That's CH3. Each one of those CH3s is a methyl. Can you see that no matter which way you number it, it's 3, 4 or 3, 4. Remember, you always start from the end. And if I come from the left, 1, 2, 3, 4 methyl, or from the right, 1, 2, 3, 4 methyl. So either way, it would be the exact same. So because they look different, but they have the same name, those are conformational isomers. Remember, you can do this because single bonds have this ability to rotate, right? So they can take that zigzag shape, or you can make them bend. So that's why they can kind of look different, but the kicker here is naming it helps you for that identification. So we did those ones. Second, well, really third isomers, conformational isomers, structural isomers. The third one are called stereoisomers. And so when you look at this, you see that this is not a straight chain. You see this if you have a ring structure. Things that are cyclo, ring structures, while straight chains, you can rotate them, pivot, you could twist it so it looks like it's going up. You can make it into the perfect little zigzag. As soon as you form it into a ring, now you lose this rotation. So ring structures have less rotation, and so any hanging groups are basically locked into position. So in this one, if you look at that three-dimensional, the ball and stick down at the bottom, can you see that the methyl group on this one looks like it's sticking up, and this methyl group off of this one looks like it's sticking down. So if you kind of look at the ball and stick, one sticking up and one sticking down, but on this one, can you see that they both look like they're pointing down? Okay, so that orientation is different, and in fact, no matter what you do to the ring, you can't make the one that's pointing down point up without changing the other one. Like I could flip it over, but then they both be pointing up, or one be pointing down. If I flipped it, then it would still be pointing up and pointing down. So because of this, because they're locked in a position, then you need to use a term to designate the position of the hanging groups. So first, what would I call these? Both of these have the same name. They're both cyclo what? These are both cyclopentane, right? Because that's a ring of 5. So if you count, it looks like a little pentagon. Cyclopentane. They both have CH3s. They have 2 of them. A CH3 is a methyl. So they have 2 of them, so we know it's a dimethyl. And then where would you say in terms of numbering? They would be what? 1, 2. Remember, when you're if you're going to name in a ring, you always start at a functional group and you always want the lowest number possible. So this would be like carbon 1, carbon 2. Whichever one you picked, you would just always go to the other methyl carbon to put number 2. So this would be 1, 2, dimethyl cyclopentane. But because I have this difference in the position of those methyl groups, I have to indicate what they are. So the one where I have one up and one down, they call that trans. The one that they're both pointing the same direction, I call that cis. So the way that I've remembered it or learned it when I first learned these is I always think of cis as on the same side. So they all sound the same. So cis, they're either both pointing down, they're both pointing up. So notice in these, you're either going to have 2 wedges or 2 like dashes, the like wedges or the dash, dash, dash. So you'll either see 2 of these or you'll have 2 of these. My pen doesn't want to do dash, dash, dashes today. Okay, so I'm either going to have one or the other. So you'll see kind of like these little wedges. And remember that a wedge is like indicating it's pointing towards you. So if I took this ring and held it flat on the board, wedges means that the non-hydrogen group would be sticking out. The dashes would be showing that they would be like pointing backwards. So I think of cis means they're on the same side. 2 wedges, 2 dashes on the non-hydrogen groups. So you just name them and then look, do I have 2 wedges? Do I have 2 dashes? Then they're cis. Trans, on the other hand, I always think trans as being like across. Okay, like trans-America is to go like from California to Virginia. So you go across America. So always think like trans, they're across from each other. They're on opposite sides. So one will always have a wedge. The other will always be the dash, dash, dash. So one will have the wedge, the other one's going to be the dash, dash, dash. I think they try to get you to draw one of these. You can find like under the little bonding in the chem draw, if you click on the little single bond line, it gives you lots of options of bonds and you can choose the wedges and the dashes. So that's actually how I did this one. So I built this one using the little chem draw. Okay, so you tell me, look at your page, you tell me what's the name. So what's the name? Yay. Okay, 1, 2, because they're on carbon 1 and carbon 2. Dibromo, because there's 2 bromines. Okay, now you could do even if the bromines were on opposite sides, like I know I've been putting them side by side, but you could still have cis and trans if like the bromine was on carbon 1 and carbon 4. Okay, but they would just both have wedges for this one. They would just be on exact opposite sides of the ring. You would still name it exactly the same way. If you have two non-hydrogen groups on a ring, then you can identify them as being cis or trans. So what's the first one? So this one would be cis, 1,2-dibromocyclohexane, because it's got the two wedges. But then when I look at the one over on the right side, that would be trans. So notice I have a wedge and a dash. So that's the easiest way to pick them out, and that's how you'll see them. So they won't just randomly be drawn, they would be drawn and you would have the wedge and the dash, because it's really the only way that you can like draw them on a piece of paper and tell the difference between them. Okay? It's just really hard to draw them like pointing down clearly or pointing up clearly. So that is where I would use the wedge and the dash for sure. Okay? So that's a cyclohexane, ring of 6 compared to the cyclopentane. I don't think that's it. I guess so. There. I knew that there was like a, okay? So in this, they're trying to show you how they could draw it a different way. I just feel like it gets kind of convoluted when it's drawn like this to pick out cis and trans, so I'll always use the wedge and the dash just because I think that makes it a little bit easier in identification. Double bonds, you don't have to name, but I will show you that double bonds end up having this same conformation. If you have a carbon with a double bond to another carbon, it also loses this ability to rotate. This literally makes them, the group sticking off of the carbons, they're stuck, okay? They're sort of sharp. You can't twist them at all. And so notice in this one, if both of the non-hydrogen groups are sticking off the same direction, that's considered cis. If they're sticking off on opposite sides, then that's going to be trans. So we will talk about this in chapter 4, because where have you heard trans in terms of nutrients? Trans fats, okay? So have you heard of trans fats? So they like had this really bad rap. They're actually now banned from snack foods. Unfortunately, when you fry stuff, you still make trans fats. So there you go. Have that with your French fries today. So trans fats, though, we'll talk a little more about them as our group of fats, oils, and lipids in terms of that discussion, because this is really like a topic where you're taking like liquids and converting them to solids, doing some of the reactions to organic molecules, like trying to make margarine or trying to make Crisco. So those are the reasons for them. All right, so the last thing. Last topic in chapter 4. Last topic in chapter 4 is a fourth kind of isomer. Okay, so the last one, so we had conformational isomers, structural isomers, stereoisomers, the cis and trans, and you'll only see those with rings. You don't have to worry about double bonds ones. And then the last one is what they call enantiomers. So they found that there were certain molecules that even though they were connected exactly the same, they had non-superimposable mirror images that actually had different properties. So one example is limonene. So limonene is a molecule that one of the enantiomer pairs smells like a fresh cut orange. So you know, like when you go to peel an orange, you know that like smell of the orange? It's like real strong. Like I walk in the kitchen, I can tell if somebody's peeled an orange. That smell kind of lingers. So that's that really nice fresh orange smell. The other version, though, which is the exact, still limonene, smells like turpentine. So turpentine is like paint thinner, okay? Yeah, she's like, that doesn't sound like that would be something you'd want to walk into the kitchen and smell on a regular basis. Not really fresh, but there's actually same number of atoms, same bonding arrangement. But because of one difference between these two, they have those very different characteristics. So your olfactory receptors can tell them apart. Your olfactory receptors respond to them. One of them smells like the other oranges, the other one smells like paint stripper. Okay? So the reason why is because of this, is because of what they call a chiral carbon. So I really wish they would have picked something else, because they use one with the bond, with the ring, that makes it an even bigger challenge. So chiral carbons are carbons that have two characteristics. They are carbons that have 4 single bonds and all of the groups attached above, below, left, and right, which is how we draw them, like with the Lewis structure. So you have a carbon, you have a bond up, down, left, and right. All 4 of those groups connected to that carbon are different. So this would be, and one that we did in lab, is we had a carbon, we put a hydrogen sticking up, we had a chlorine to the left, we had a bromine hanging down, and we had a fluorine to the right. So that one's pretty straightforward. You can clearly see that each atom connected to that carbon is different. So when you made the mirror images, you set them up so that you then made the hydrogen was still sticking up, the bromine still down, but then the chlorine was on the right, the fluorine on the left, making them look like mirror images. You could not pick them up and lay them on top of each other. They were what they said, non-superimposable. So they're actually different. They're different because the bonds, you can't match up those 4 groups. So now we literally have like a left-handed version and a right-handed version. Right? So you kind of think in chiral, the term chiral means hand, because if you look at your hands, when you hold them up, palms flat, you can see that they look like mirror images of each other, but you can't lay them on top of each other. So they have handedness. I have like a left-handed version and a right-handed version of this molecule that are a little bit different. They're not identical, just like your left and right hands are not identical. So when trying to find a chiral carbon, I find it's easiest just to throw out the ones that it cannot be. Okay, so if you look at a molecule that has 4, 5, 6, even could have 10 carbons or more, you look at each carbon. Any carbons with more than 1 hydrogen directly connected, you can throw that out, okay? So it has to have, or you could throw out carbons with more than 1 hydrogen. So if you have a CH2, can't be chiral. If you see a CH3, can't be chiral, right? It can only be a CH maximum. So more than 1 hydrogen, you can't make non-superimposable mirror images. Those mirror images, I can make them match because 2 of them would be identical. So I could match the other 2. Have to have less than 2 hydrogens directly connected to the carbon, and you cannot have any double bonds. Any carbons with double bonds, even carbons with triple bonds, which we really don't see very much, but if it doesn't have 4 single bonds, then you can throw them out. So for example, if you see this, you know you can throw both of those carbons out because they both have double bonds. Or if you see a carbon double bond into an oxygen, you can throw that one out because it's got a double bond. So it has to have 4 single bonds attached. I will use Lewis structures, and I'll show you some of the examples with the others and why it gets a little challenging, but I will use Lewis structures to show you these on an exam. So a Lewis structure would be something like, you would see it just like this. So you would see them all drawn out clearly, okay? So that you can look at each carbon and look above, below, left, and right. So when you're sort of evaluating or inspecting, here's a carbon. So when I go to ask myself, are all 4 groups different? The question is this group, this group, this group, and this whole group. Okay, so it's not just the carbon to the right, it's everything to the right, everything to the left, everything above and below. And do you see that all 4 of those are different? Yes. So that would have like a little, they like to put a little asterisk next to it. So yes, this would be chiral. So let's look at the one that's on the right. So when you look at the one that's over on the right, I'll just change colors. Now I'm looking at this carbon. So what's above? An OH, not just an oxygen, but actually the whole thing would be an OH is above to the right. There's a hydrogen below, chlorine, and then to the left, is that whole big group. So the question are all of those different? Yes, okay. So this would also get a yes. So it's not just what's directly next to it, it's everything, the entire group to the right, left, above, and below. And that's why I like drawing it out in a Lewis structure. I think it's a little easier to pick it out. So let's look at a couple of these. So what would you tell me about butane? Are there any chiral carbons in butane? Why? They all have what? Okay, they all have more than one hydrogen. Can you see that? When you look at every single hydrogen there, do you see that every single one, there's more than one hydrogen? I have 3 hydrogens, 2 hydrogens, 2 hydrogens, 3. So there's none, okay? None of the hydrocarbons are chiral. They're not going to have chiral carbons. You're not going to deal with chiral carbons there. What about the one that's on the right? So let's look at them individually. So that, would you say that's chiral? Why? 3 hydrogens, right? So remember, more than one hydrogen directly connected? No. It's got 3 hydrogens. What about the middle one? Why? Because it's not just 2 carbons. What's the group on the left? A methyl or a CH3. So remember, it's all of this. So there's a CH3 to the left. What's above? An OH. What's below? So see, those 3 are different. But then what's the one to the right? Another CH3. So do you see that these are the same? The groups have to be different. So I have a CH3 on the left and the right. So this is why that is not chiral. What about the carbon on the far right? No, it has 3 hydrogens, right? More than one hydrogen, it can't be chiral. So this would also be, you would say there's no chiral carbons in this molecule. You just look at each one. So when you look at ones like this one straight down, the reason why, because it's a sugar, okay? So this is a ketopentose, a 5-carbon sugar we'll talk about in chapter 6. But what would you say about that first one, that top carbon here? Could this be chiral? Why? Because you see H2, so remember written in condensed. So if you see an HCH2 or CH3, you know it can't be. So this is no. It's got 2 hydrogens. What about this one? Why? Double bond. So carbon cannot have a double bond. So going down now, the third one. This one. To the left is a, to the right is a OH. Above is a 2 carbon, 3 hydrogen, 1 oxygen. Below is 2 carbons, 2 oxygens, but then 5 hydrogens. So are they different? Yes. Do you see that the groups above and below, they have a different number of atoms, different bonding arrangements? So yes, that is chiral. What about the next carbon down? So again, I'll try to change colors to show. To the left, to the right, below, and then everything above. What do you think? They're all different, right? So I have an OH, an alcohol, an H, a CH2OH, or a 1 carbon, and then 3 carbon group above. So yes, so you would say that this molecule has 2 chiral carbons. That's a TWO. Okay, look at the one that's kind of underneath, the one with none to the right. Now this one, like sometimes if you take this CH, remember that means that that H would be up here, right? So if it's a CH, then same thing here. So this one, this would be an H. So the end carbon, CH3, can it be chiral? No. Why? 3 hydrogens, right? So I know this is a no. Do you see any others it can't be chiral? The one on the other side. So you see the CH3. So like you can throw out anything that's a CH2 or a CH3. You know that that can't be. So then we're just looking at the middle one. So here's one of the middle ones. So that carbon above is a hydrogen. Below is an alcohol. To the left is a 1 carbon group, right? Because it's still the whole thing. And then to the right is a 2 carbon group with an alcohol. So are all 4 of those different? Yes. So that, we get a little asterisk, Yes. Then examine the last carbon that we haven't done. Is it chiral? Hydrogen above, single carbon to the right, alcohol below, and that whole group to the left, the 2-carbon group, those are different. So you don't have to identify them. It's really just think of like circling them. So if you don't want to circle them, just look above, below, left, and right, and you're like comparing. Do they all look different? It's not just the atom directly next to it, it's the entire group to the left, right, above, and below. So this also would be a star. So you would say that's 2. Okay, this one's vitamin C. So this is ascorbic acid. So vitamin C, they have it drawn, and this is why I won't do this to you, but they have it drawn as like a skeletal structure. So even if they have a skeletal structure, but there's things other than carbon and hydrogen, they include it. So those alcohol groups, so see the 4 OH groups, those are alcohols, okay? This group is a what? Look at your functional groups. What is that one? Nope, it's close. It's a ketone, but it's got that oxygen in the chain, so it's a ester. Look at the ketone versus the ester. So that double bond oxygen is going to be one of those because it's in the middle of the chain. It's in a ring. But then since it has that oxygen next to it, it's an ester. But now remember, every corner other than carbon, 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 every corner that doesn't have an oxygen on it is going to be a carbon. So there's 1, 2, 3, 4, 5, 6. So which carbons can I throw out? Which ones do I know can't be chiral? Anything that has a double bond attached. Right? So I can go back and say no, 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 right? Because those ones, anything with a double bond attached, you can automatically throw out. So that just leaves 3. So let's look at the top one. So carbon, how many bonds does it have to have? It has to have 4. So see that top carbon right here? See that it has 2 lines attached, so how many hydrogens would I have to add to it? 2, because I'd have to make the 4. So what does that mean this is chiral? Cannot be chiral because it's got to have 2, so this is a no because it has more than 1 hydrogen. That just leaves these last 2. So this carbon below, how many hydrogens would it have? 1. And this, how many would it have to have? 1. So when you see just 1 hydrogen, those are the ones that are more interesting, right? Because you don't automatically toss those out. So when you look at these 2 carbons, so looking at this one here, I have a single carbon group with an alcohol, a hydrogen, an alcohol, and this whole thing. Are those all different? Yes. So that is a chiral carbon. So that means that I can make a right and left-handed form of vitamin C. And very interestingly, in nature, it's usually one or the other. So in nature, you don't end up with both. So like for sugars, almost all our sugars are D sugars. So those are sort of like the right-handed form of the sugar. They just exist that way in nature. Amino acids are almost always the left-handed form. So they're actually purposely made so that they fit together. They don't have bonding issues. So the last one is one of the reasons I won't give you a ring structure. So the last one, I can tell you, if you look at this last one, see if I can change the color, you can see. I'll do green, okay? So you do see there's a hydrogen. There's a 2 carbon group sticking up with a couple of alcohols, right? But then the other one, because it's part of the ring, when looking at this, if I go this way, I encounter an oxygen first. And if I go this direction, I encounter a carbon first. So because the order of the atoms is different going around the ring, that would be considered chiral as well. So this one, ascorbic acid, vitamin C, actually has 2, but I won't ask you that. And I won't give you the skeletal structure because when you have a skeletal structure, you have to go back in and like put those hydrogens in. You have to remember carbon's got to have 4 bonds. So if I don't see hydrogens, I actually have to go put them in. So these are kind of good examples. I think that your book has you do, or your mastering has you do 1 or 2. So the connection with this, what they call the consequences of having these right and left-handed molecules, is that receptors, medications, that they actually are commonly have a chiral carbon. So that means that they have the handedness. So like by example, so like if someone comes to shake your hand, that feels normal, okay? Same thing, put your same hand out. And someone goes like this, how does that feel, right? That's really like the logistics. Like when you go to shake hands, you shake hands with your right hand and you match their right hand. But somebody like sticks their left hand out, you like grab the back of your hand and you're like, thank you. That's very strange, right? It feels awkward. It doesn't fit together. Same thing, like interlock your fingers, right? There is a certain way you interlock your fingers. I am right thumb up. Do it so your other thumb is up. I can't even do it. Huh? Okay, so yeah, so, and that's genetic. I'm right thumb up, but switch it so you put your opposite thumb up and change the lock interlacings of all your fingers. Does that feel strange? It feels to me like I'm holding my hands like this instead of being able to put them together. They like don't match. That is kind of what chiral molecules are like, is you end up with this right and left-handed form that just, like they have a specific function and their shape is really important. So the Food and Drug Administration now has part of their law, if there is a drug, a medicine that is going to be used for any living creature, and there's a chiral carbon in the molecule, it must be identified. You have to synthesize all the enantiomers. So you have to make the right and left-handed versions of that medication, and they all have to be tested. So, a couple of examples. So one, dopamine, destruction or loss in the brain leads to a disorder that is called Parkinson's. So dopamine has a lot of jobs in the brain. It's involved in mood, memory, but its big function, and the reason it starts to be identified, is because it helps to control very fine motor movement. Okay, so when you think about like trying to like color in and like stay in the lines kind of thing, like get exactly right, that's where dopamine comes in. So it helps to like fine control your muscles, that the stimulus sent from the brain. So somebody with Parkinson's with loss of dopamine, you begin to lose that. So one thing you might start to notice, they might to develop a tremor. So they may have like a hand tremor, or they may end up starting what they call pill rolling. So you'll see that their fingers will just start to do this sort of like circular motion over and over and over again. Sometimes they start to develop like a little head wobble, okay? And that's literally that the stimuli, maintaining posture, maintaining just random movements, it's not being sent out as smoothly as possible. So those muscles are like partially relaxing and contracting a little out of sync, which creates that. They didn't really understand all of what dopamine did when they first discovered Parkinson's. They just knew that people started off with this wobble, that they began to lose their coordination, that they were now fall risks. Worst case, they eventually lose mobility. So then they're in a wheelchair, and then they become less and less responsive. So they almost like become just like comatose. They're like considered like little vegetables. So they don't like move, interact, respond to things. So in this discovery of this is what's going on, they developed a drug. So this drug is called L-DOPA, okay? So if they gave the patient dopamine, your brain's really protective. You have what's called the blood-brain barrier. So this is really an extra layer of cells that controls what can go from your bloodstream into the area around your nerve cells in your brain. So there's not everything can pass the blood-brain barrier, and dopamine could not. So they would give the patients dopamine thinking, well, maybe this will help, and it had no effect. Even though the dopamine was like levels were in the blood, the levels never built up inside of the brain. So then they found, well, if we don't give them dopamine, but we give them the thing that gets made into dopamine in your brain, which is why they called it DOPA. So it's actually like a precursor. It's kind of like the building blocks to make dopamine. That can cross the blood-brain barrier. But they found that there was one chiral carbon. So now we have a left-handed and a right-handed form. So they found if they just gave the patients randomly this DOPA, it didn't have much of an effect. They found that The left-handed form, they call it L. It doesn't mean left, but you can think of it that way. The L-DOPA, this is the one that has biological activity. This would get converted to dopamine in the brain, and suddenly these people woke up. So these people had actually still been aware of what was going on around them. They just couldn't respond because of lack of this neurotransmitter. So this is one of the meds that's given to people early on to try and decrease the change that occurs in that part of the brain where dopamine is typically made. Unfortunately, the other one, so the right-handed, they call it the D form, has no function at all. So if they gave them the L form, they had positive reactions. If they gave them a mix of the two, they got minimal results. So once they realized that there was only one form of the drug that they needed to use, then they wouldn't use this. They would instead just synthesize the L form, one chiral carbon, like one side of it, and that was given to patients and had a great success. Just a couple of others that you're probably a little familiar with if you've ever had bronchitis, ever had any respiratory issues, if you've ever had kids that get the croup, they give them albuterol. So albuterol is an ingested bronchodilator, okay? But looking at this one, can you see here the chiral carbon? So that one right there, so there's an alcohol up, a hydrogen down. To the right is a nitrogen 4 carbon group. To the left is a phenol ring structure group. Can you see how up, down, left, right? Same thing with albuterol. One form of albuterol has that bronchodilator capability. The mirror image doesn't do anything. So the shape of a molecule is really important. Other ones, naproxen, like if you've ever taken Aleve, ibuprofen, which is Motrin, both of those also have chiral carbons in the same thing. So you find the same function. One of the chiral carbons has biological activity, reduces fever, reduces pain, decreases inflammation, but its chiral mirror image doesn't work at all. So it's like that important in terms of like how critical they can be. Unfortunately, this really is more important in certain medications. So notice with the ones we've just talked about, one form works, the other form doesn't do anything, okay? So using the right mirror image form, the right enantiomer pair of a medication can be critical. But in the late 1940s, early 1950s, there was a drug that was developed called thalidomide. So thalidomide, and there's the two structures, the thalidomide, when it was tested, they only tested one enantiomer pair. The fact that it had a chiral carbon was not identified. They tested the one enantiomer pair and found that it was really effective at reducing morning sickness. So some people don't really have morning sickness at all. Some women like get really sick. Some women end up having to be hospitalized and be on IV therapy because like they literally can't stop vomiting and so they get dehydrated. This really made a difference for patients that were having those type of like extreme morning sickness. And that means that you don't lose weight. That's better for baby development. And so long term, like that's just a better pregnancy outcome. So they ran through and they made the first enantiomer pair and they ran through the clinical trials, had very positive results. Then they scaled up. So if you ever like made a single batch of cookies and then had to make a triple batch of cookies and you're like, this is just not as good, right? Right? When you scale up sometimes, like you kind of lose it. So that's why like the small batch stuff is kind of like the fancier stuff now. Doing things in smaller batches compared to this large scale. When they scaled up, instead of making the single enantiomer pair, they made 50% of each. So they ended up making the enantiomer pair that affected and really decreased morning sickness. Unfortunately, while most of our meds that we've been talking about, the other mirror image has no function, this mirror image was actually damaging. So the thalidomide, the mirror image of the one they tested, was found to be teratogenic. And teratogenic just means it has the ability to cause birth defects. So unfortunately, you're giving this to mothers during the first 3 months of pregnancy, which is when a lot of embryonic fetal development is all going on. So thalidomide, the right-handed form, actually affected what happens during about the 7th to 9th week. That is when you go from looking like a little tadpole, because you have kind of like a head and then a little spinal cord that's starting, but then you start what they call limb elongation. So this is when the arms and legs, they start like literally like little buds, and then they extend out, and then eventually you'll have hands, you get the little leg buds, and eventually you'll have legs and then feet. Well, thalidomide inhibited limb elongation. So what ended up happening is you ended up with about 10,000 babies that were born someday. 10,000 babies that were born in the early 1950s that had severe limb deformities. Many of them were born with like hands attached to their shoulders, or they had like what they called them flipper babies, because they had like literally just like little extensions off of their arms and legs. Only about a half of them survived, because along with like the limb deformities, a lot of times their pelvic floor did not form correctly. So they didn't have all the normal like urethra, anus, they didn't have all those normal structures. And so in the 1950s, there wasn't a whole lot of surgeries and things that they would be able to do to be able to remedy that. So this was an example where there wasn't in the 1950s, kind of like with the x-rays and people taking x-rays of their feet in the 40s. Okay, there wasn't a lot of like this knowledge of safety, this knowledge of testing, this knowledge of making sure that the public is always like protected from any type of medications. And so this is why the FDA now has the rule that if you're going to submit a drug to even start testing, you have to completely know the chemical structure, you have to identify any chiral carbons that are there, and you have to be able to synthesize all mirror image pairs. So if you have one chiral carbon, you got a pair. If you have two chiral carbons, now you got 4. If you got 3 chiral carbons, now you got to test 6. So when you talk about how many billions of dollars it takes to get a drug to the market, there's a lot of reasons behind it. And this is one, is because of without having those safeguards in place, there can be all kinds of problems. And the reason there were 10,000 is, think these women were given thalidomide in the first 3 months of pregnancy. They didn't know that there was a problem for another 6 months. And in that time, more women were prescribed thalidomide. So you went through like multiple rounds of thalidomide before babies were born, before doctors started putting it together that like, okay, what was unique or different about this mother, and this mother? Because in the town, these were the only ones that ended up with this issue. And that like led back to they had more severe morning sickness and they were prescribed thalidomide. So that's just like one of the important things about one, making sure you look at labels, and 2, like this understanding like drug development really doesn't just like come straight off really, really quickly, that there's a lot of steps that have to go into play. All right, so go ahead and look at the last one on here. Take a minute, 1, 2, 3, 4, 5, 6 carbons. Tell me how many out of those 6 carbons are chiral? So how many did you get? 3? Did everybody get 3? Good? Okay, first one you're going to toss out, why? 2 hydrogens, right? Right? Can't have 2 hydrogens, can't have 3 hydrogens. And this is like a good example of what I'll give you, okay? Like I'll have it out like a Lewis structure, okay? So you'll have carbons up, down, lines up, down, left, and right. What about carbon number 2? Nope, it's got a double bond. What about carbon number 3 then? Nope. Okay, so I can toss all of those ones out. So those are the ones going down. The next one's a Br with a hydrogen. The next one's a chlorine with a hydrogen. The next one's a hydrogen, chlorine, and an OH. So those ones I got to look at. I can't throw those ones out instantly. So what did you think about this one? Chiral. Hydrogen up, bromine down, 2 carbons to the right, 3 carbons to the left. Okay, so yes, that one's chiral. What about the next one? Okay, so when I look at this one, chlorine going up, hydrogen going down, single carbon to the right, 4 carbons to the left. And like literally you can just, if you see that there's definitely different numbers, then yes, they're got to be different. So yes. And then the last one. Yep, hydrogen up, chlorine to the right, alcohol, hydrogen, alcohol below, and then a big 5 carbon group. Yes, so you would say this has 3. Okay. I will save this. This will the image of this will get posted so that if you want to go back and look at it, but you can go back and do the practicing. Remember, there's those blank PowerPoints. You can always go back and practice doing naming, identification, because I think there's quite a few examples in there. Keep this, okay? Tuck this to the functional group page. You may want to add your own notes to it. When you come to take your test, you'll have the laminated version, but it's pretty much the same, okay? 2 weeks from today. What's today? Today's Tuesday, right? Yeah, 2 weeks from today. Okay. No, it's not a week from today. I'm we still have to cover 2 chapters. We got to cover them fast. Okay. See you later.